For number 8, we're trying to find the probability that E or F occurs. So it could be that just E happens or just F happens, or maybe they both happen, but we're trying to find the probability that at least either E or F, maybe both, but one of them is going to occur for sure. And to find that probability of two events like this, you add together the probabilities of each individual event and then subtract the probability that both events happen at the same time. So the probability that E and F are simultaneously occurring. So add those together, subtract when they both happen, and you'll get that. A visual example of that: E occurs 0.25% of the time, and they both happen 0.05. So they both happen here, E and F overlapping 0.05% of the time. So the whole E circle happens 0.25. And F happens 0.35 total, but again there's this overlap where they both happen. The whole event F happens 0.35. So visually, if you add together the E circle, the chances it happens, plus the chances the F circle happens, you'll see this 0.05 gets counted twice. It gets counted when E happens. It also gets counted in the F circle. So you got to subtract it because we don't want to double count the likelihood of this. For number 9, we're given several facts about events E and F. The piece we're missing is the probability of F, and we can use the addition rule to solve for that. So recall in the addition rule, we have that if we're trying to find the probability of E or F, we would add together the probabilities of the two events and then subtract the probability of E and F, the probability that E and F happen simultaneously. So the problem tells us 3 of those 4 pieces, fill them in where they belong, and then you can solve for the one piece that's missing using algebra. So 0.5 minus 0.20 leaves us with 0.30 plus probability of F on this side, and then subtract 0.30 from both sides, and you get the probability of F is 0.25. For number 10, we have a sample space where all of these numbers are the only possible outcomes. So maybe these numbers are in a hat and we're going to draw one of them out. We're going to say event E is drawing one of these numbers and G is drawing one of these numbers. And then we introduce the term mutually exclusive. And what that means is that E and G are completely excluded from one another. If E happens, it means G couldn't happen. If G happens, then E definitely doesn't happen. They never happen at the same time. They're exclusive from one another. So we're going to try to list the outcomes that are in both of them, if there are any, and there are. 8 and 9 are in both E and G. So what that means is that they're not mutually exclusive because they have outcomes in common. If they had no numbers that were similar, then they would be mutually exclusive. For number 11, the sample space are these numbers right here. So maybe all these numbers are in a hat and we're going to draw one of them out. We're going to say we hit event E if one of these numbers is drawn. Event G is if one of these numbers are drawn. So are E and G mutually exclusive? They're not. Mutually exclusive means they have nothing in common, that they cannot happen at the same time. But E and G could happen at the same time if we drew the number 9. So because 9 is in both of them, if we draw the 9, then E and G are both occurring. Mutually exclusive means that they cannot both occur at the same time. For number 12, here's our sample space. So the numbers 1 through 12 are in a hat. We're going to draw one of them out. We're going to say event E is one of these numbers being drawn. E with the little C up here means the complement of E. And what that means is everything that's not part of E, or the opposite of E happening, everything but E. So if E is these numbers being drawn, then the complement would be every other number that's a possibility. So here's all our possibilities. So list every number that's not part of E. And what's the probability of getting E's complement? Well, there are 1, 2, 3, 4, 5, 6 numbers here that are not part of E that are in E's complement. And there's 12 total numbers, so 6 out of 12, or 1/2. For number 13, we're trying to find the probability of E's complement. And we know the probability of E is 0.22. And this is easiest to explain if you think of event E is the chances that it'll rain tomorrow. If the chances that it'll rain tomorrow are 22%, then the chances that it's not going to rain are 78%. So an event and its complement should always add up to 100%, their probability should. So since event E has a probability of 0.22, the probability of the complement needs to be 0.78. For number 14, we have a bag full of golf balls. There are 16 total golf balls, 5A, 5B, and 6 of type C. So 16 total. And we're finding the probability the ball is not a type A. Well, the probability of a type A would be 5 out of 16. So if you get an A 5 out of 16 times, how often will you not get an A? And that would be the remainder, the remaining 11 out of 16 times you don't get an A. So the complement of getting an A is 11 out of 16. Another way to solve this is to think if you're not getting an A, that means you're getting either a B or a C. So B or a C, there's 11 of those, so there's 11 out of the total 16. You're not getting an A, 11 out of 16.